like to the other side. Yes. Because then it's facing towards your mouth. Like this.
So, like this?
Oh, thanks.
Thanks.
Okay. Thank you, everyone, for coming after lunch. So I want to recap a little bit of what we did yesterday, just in words, and see if there are any questions about that. So we talked a little bit about we derived NTK, the recursion relationships for it. We talked a little bit about just the intuition for why it holds, but I didn't go through some of the key steps of what you would need to prove it, which I can do if we end up having more time. And then I also talked about two different parameterizations, NTK parameterization and standard parameterization, how that kind of affects the choice of maximum learning rate and stability conditions for it. And also just the fact that this result holds for gradient descent and not just gradient flow. So that's something to keep in mind. So today, I want to talk a bit about going beyond kind of NTK theory or beyond the infinite width limit, kind of with two different types of things that would be natural for a physicist to do. So I'm going to very much work in kind of like a physics level of rigor today, and hope you'll forgive me for doing that. But we're going to do both like perturbation theory away from the infinite width limit. And I want to present that because it's nice to be able to do an explicit calculation where we can calculate the correction to a kernel. I'm going to show you some of the key points where you can kind of somewhat justify it, but it's there are some reasonable approximation assumptions you can make, and then calculate a correction to leading order in width. And then, but I want to present it because it's also kind of nicely, I think, sits within this framework of a hierarchy of differential equations that are coupled that you can think about in sample space rather than parameter space. And I think this kind of connects. It's like a nice duality between a parameter space formulation of things versus a purely kind of sample space or data space formulation of things. And then I'm going to talk about one effect that sets in when networks are very wide, but you kind of run gradient descent above this critical learning rate that comes from the NTK analysis. And basically show that even if you can have a very wide network, but you really do gradient descent and not gradient flow, that you can actually get feature learning in a particular like narrow regime of learning rates. And so that kind of, this is kind of outside of the type of analysis that you would do kind of an infinite width or with gradient flow. And this is something that sort of non-perturbative effect is something that would be hard to kind of capture. It'll relate back to this hierarchy of equations that we're going to use to kind of center the discussion. Okay, and we'll get some minimal models out of that I think are interesting just for further analysis and kind of analyzing a bit more rigorously. Okay, so just to recap, so we're doing ERM. Sometimes I'm going to work in continuous time, sometimes discrete time. We have equations like this for just full batch gradient flow. To save myself a bit of writing, I think, although I don't do it in my notes, I'm going to define this to be R sub alpha. We're going to do an exact calculation for square loss, so I put R to think of kind of the residual, because that's just a term that's linear, and it's going to be F minus Y. Okay, theta you know. And so what I alluded to last time is we're just going to continue this program of differentiating kind of down this tree. So we have theta as a dynamical variable. And we do this, and we play the same game where every time we write ddt, it's really dd theta times theta dot, because all of the time dependence comes from evolution of theta. And then from theta dot, we're going to split everything into dependence on the function and dependence on the parameters. So probably you don't need to see me write that again. We did this yesterday. So let me write it like this. And I apologize, there are going to be a lot of indices in this lecture, because the calculation is sort of the thing of field you would do in like field theory, where you have a lot of indices on your tensors and you're going to contract them. Okay, so this is everything that looks like DLDF, and then everything that is derivatives of the function contracted over all the parameters. So it's something that's only dependent on, the samples, which could be coming from the data, but we could just leave them as arbitrary inputs. Let me define this as O3, x prime, x alpha, but this is just because I plugged in alpha here. This could be x double prime. So it's just a function of 3 inputs. Okay, so we have this next level equation. And in general, there's, it's not that all these indices are necessarily symmetric. So the kernel is symmetric in x and x prime, but as you go further down, there may be other kind of symmetries, but it's not in general. It's kind of symmetric about all of them. Okay, so let me define, following this type of program, I'll call these operators, but they're not operators, they're just functions of S inputs, and that's the subscript here, OS, in the following way. Okay? So that fits our definition of O. So let me define O2.
Just one thing over there. This definition of the change of the kernel, the second derivative of the function is evaluated on x alpha or on x?
Did I do this wrong?
Yesterday we had x alpha, like the training sample, and the quadratic form, the two terms, they were the test points x and x prime.
It would take us 1 minute to do it. No, I believe this is not, actually, let me.
So it does not, the change of the NTK would not depend on the data samples do not enter through the second derivative of the function.
I think they don't, but I need a minute to work it out from in my head. Yeah, I believe they don't. Does anybody else disagree with what I wrote here? Okay, let me. But it just came from DDT on the definition of theta, and then so let me write what's actually being substituted. So this is the first step, but really this is also So this is the operation that's happening with the minus sign. Okay, so let me define O2 to just be theta also. So those are all our operators. And then we have the following equation. So okay, and you can check, imagine plugging in OS plus 1 in here. You can just check that you recover the DDT. So this, as a reference for this, I'm taking this from and then there's also a math paper, which is kind of like a physics formulation of it and more mathematically rigorous thing. But the exact calculation I'm taking is from this first reference. Okay, so in principle, we have this hierarchy of coupled equations. You see that I'm going to kind of write down. We have the top level equation, which is df dt. Okay, let me skip writing all of this out. But you can kind of think of it, it has a nice physical interpretation, although I'm not going to use this, of kind of interacting where the samples or the inputs are interacting particles. So we start with kind of a top level equation, which is we have one input, x, df of x dt, which we relate to some kind of two particle thing, which is theta. And then at the next level, we relate kind of this two particle object to a three particle object, and 3 to 4, and so on. Out of curiosity, does anybody recognize kind of, or does this remind you of any form of equations from physics? Which I don't believe it maps on exactly, but there are some other things that kind of have a similar form of multiple particles. So it reminded me of this BBGKY hierarchy. Does anybody know this from non-equilibrium stat-mech? But I just mentioned that as a remark. We're not going to actually use this here. Okay. Now is the part where I use a claim from these papers. I use it from the first paper, where okay, this is the part where, okay, why is this true? So first of all, it's kind of, if this were t equals 0, so these are these O operators. This is kind of an arbitrary function here. This is the statement in the paper, but really the function that we just care about is this residual that we're going to use it against. If this were t equals 0, this is coming from some estimation of the way that different gradients and kind of derivative tensors of f scale with n. So if you think back to kind of the Wick's theorem calculations we did earlier, so when we take derivatives of the network function f, we start to get, we get derivatives, but we also have sums because these things are summed. So for the sums, there are factors of n, and then for the derivatives, there are like factors of 1 root n from the NTK parameterization. Right, you remember this? And that's the sort of thing that makes theta order 1 at initialization, and it makes O3, suppressed by some order, and so on. So this is just an estimate from initialization. And then the sort of the part that's non-rigorous in what I'm quoting is if you, now is it true for general time? So you know, it's over the initialization, yeah. But the idea behind how it was originally justified is that you imagine Taylor expanding in T. So there are more kind of derivatives of these operators that appear. Those are also kind of suppressed similarly with the same O. So if it's analytic in T and you can kind of expand it, then the claim is that, okay, these things scale in this following way. If it were T equals 0, it would be fine. Now, the part that I think is...
What is F here?
F is kind of an arbitrary, they put it as put in kind of an arbitrary function, but we're going to use this to kind of apply to R. So the rough idea is, the way we're going to think about this is similar to the rough intuition I gave for NTK, but which is that, you know, at t equals 0, this is something like f minus y. So it's something that's order 1. And as you go on with time, you know, this, if the loss is decreasing nicely, rapidly enough, then this sort of thing kind of, you might hope that it would continue to be true. Right? So if the loss starts to have kind of, either you go out to infinite time and you're kind of getting, you know, you're summing over enough things in such a way that you're breaking the one, that you have like factors of n appearing, then this is the sort of thing that would break this. So that's sort of implicit in this. And so, you know, although, as I say, it's not rigorously proven in where I'm taking this from, imagine if you have this kind of exponentially decaying with time, like this residual. So you kind of expect that the 1 over n scaling would persist.
Yes, well, can I ask, am I misremembering in their paper, if t equals 0, they check it for some kind of networks, but not for others? Is that right?
This?
Yeah.
So
Linear maybe? Or?
that's right. So this, in the original paper, was for deep linear networks, and I think one single hidden layer with smooth activations, and then conjectured for ReLU, and then maybe since then has been extended. So there are more rigorous versions of this in this paper. But this paper doesn't have the calculation that I'm going to do. And so what I want to do is like do this calculation. We'll get an answer. It'll probably be valid out to some time. Now, if you want to be really rigorous about it, you want to prove that it's valid for all time. And that's like probably more work. So that's the way I'm going to justify this perturbation theory. Any questions about this? So let me do the pedantic thing of writing all this out just so we can stare at this. So I can stare at it. And then reference it later. So okay, so we're going to work to leading order in 1 over n. So I'm going to basically, this is the sort of thing that we're going to apply, and it's going to allow us to drop basically O5. So this, let me take a step back and actually say something about these differential equations. So this, it's not obvious to me that these equations truncate in any natural way. What I'm showing you today is one effective truncation that's coming from backing off of width, infinite width. So we're going to truncate it at some level around here, and then compute a solution. There might be other truncation schemes that are possible. Maybe as you go further down, there's something funny that happens with having too many samples. It doesn't naturally truncate in the sense that if you look at these O operators for much lower in this hierarchy, they consist of high derivatives, like this one, contracted with these low derivatives. So you might wonder, okay, maybe at some point I take too many derivatives of f and it truncates. But I actually believe that there are other terms in there that actually consist of contractions of low-order derivatives, which persist in a general nonlinear network. So you might not need to like assume some things to get it to actually truncate just from this differentiation. Any questions so far about this? So the idea then is that we are going to think of each O as having different contributions of order R, where OSR is something that scales as n to the minus r. Okay, and so like F is going to have some expansion, with the leading corrections, with the leading order term and corrections. Theta or O2 will as well, and O3. Okay, so now let's do one actual calculation for this hierarchy to leading order in 1 over n. So let me take loss equal to this. I'm going to drop my 1 over m in terms of number of samples. The first equation is this one. So again, imagine I take, here's where I use this justification. Imagine I take expectation of this thing over theta naught. Okay, so I said that that thing was order 1 over n squared. And as long as this residual is not, gaining some weird dependence with n, then this sort of thing you would kind of expect to hold maybe for all time. So this is something that is, I'm dropping things based on their expectation value is sort of what's happening in the background. So this is O of 1 over n squared. So O4 is just a constant. Okay, and so how about this one? I won't write all the indices, I guess. Okay, so this is something that has something of this form. Now, not number, but it's, I'm not treating it as putting in the randomness, but this is something that is, O of, when I say O, I mean it's actually 1 over n plus the higher order stuff. And this thing, we know the NTK solution, so that's correct to order n0, order 1. So think of it, related to that expansion that I wrote there, think of it as something like this, or this is how a physicist would think about it. So to be correct to order 1 over n in this whole thing, I can drop these other corrections to the NTK dynamics. So I'm not going to put those in. I can just get away for right now by plugging in the NTK solution with time. So reminder, what is that? Let me write it in this form where I don't put any indices on it. There's just going to be, I'm doing full batch gradient descent. So these are just matrices and vectors evaluated on the data. I'll use it as my shorthand. F0 here is referring to the fact that it's leading order. It's referring back to that R. And also we have, we know that this is also true. This we'll use in a minute. But so I can plug this in and do this integration with time. Okay, and when you do that, so it's just a single e to the minus t that you have to integrate with time. It's easy to integrate. And so you get where, let me now play around with my symbols a bit. So, and I'm going to do this multiple times. So let me let this x vector tilde denote this triplet here. And then I'm thinking of this as a vector on the fourth index that's being dotted into the fact that this is, this is a vector on the data space. Right, so there's one contraction that's happening here over the data, and this is the NTK solution, which is over the data, and then there are these three free indices, free arguments, x1 through x3. Oh, sorry.
For O4, you need another sample.
Say that again?
For the O4, you need one more sample.
We do need one. I've kind of taken it into the vectorized form. So let me,
Just have x1 to x3, right?
yeah, let me define. It's sort of this is a scalar. This is a vector. Let me put like a strong dot here, which means that I dotted it in. Okay, so this is the correction for O3. Now we do the correction for NTK. So this is just the t equals 0 value at finite width. So maybe I actually should have said this a bit earlier, so I apologize. So there are multiple sources of correction that are happening here. There's one correction that comes from you have NTK at infinite width. It's deterministic. You take it to finite width, and it's a random variable, and its moments kind of depend on n. What is kind of happening in the background here is that we're working at slightly off of infinite width. This is still a random variable, but I've kind of evaluated at t equals 0, so I've quenched it. So I'm just kind of fixing things at initialization and then finding the corrections kind of just that comes from dynamics and dropping things based on the scaling of the expectations that I gave you. So this is really, this theta 0, is a finite width NTK at t equals 0. And same with all these other t equals 0 operators, they're finite width things, which in general they would be random variables, but I've quenched that part of it. I've just initialized. Okay, so we're going to compute theta 1. So let me just be super pedantic about this step. So this is 0, because the initial value of theta is just this thing, kind of by construction. And what I need to do is compute this integral. Okay, again, I plugged in the NTK solution here. Why? Because this is something that is like, you know, in general, it would have been, if it were the general and time solution, it would be something plus something of order n plus other stuff. And this thing itself is something that's 1 over n plus 1 over n squared. So again, I can get by just dropping this thing, if you'll allow me to do that. So I've plugged in the NTK solution here. And this we have from this equation. Okay, so this is just the one last step of kind of doing a calculation where I have something that is exponential in time. I'm going to plug it into this, which is also exponential, which this is going to be exponential in time in t prime, and do this integration. Is everybody okay with this? Okay. To make it easier, because I would like to write out a final form that we can just stare at, because purpose being that physicists like to have kind of a nice, okay, maybe it's not always useful, but to have kind of a nice closed form expression for things. So, you know, the expression I write down, then you can do further analysis of it, you know, with a small, small correction on NTK. And I know, I mean, you can already see we can do all these time integrals easily because they're like nested versions of exponentials. But let me just kind of, if you'll allow me, walk through kind of the final steps of this. So to do this easily, when we plug in NTK into here, it's nicer just to do, decompose this in the eigenbasis of theta naught. So let me let lambda I EI be coming from NTK. And let this delta F not be the residual evaluated on the training data. Okay, let me actually I'll skip the writing out the intermediate steps of the integration, just write the final form for this correction. And then we'll basically be done. Yeah.
So in theta 0, are you using the actual infinite width limit, or do you have to keep...
No, yeah, it's not it's the finite width version of it.
Okay. So you cannot replace those, eigenvalues as if it were the n with additional corrections.
It's sort of like if you were going to go, I believe, so I'm not the... this is what my mental model of what's happening in this calculation. So I believe this is the finite width NTK, so empirically you would just go evaluate it at initialization. You would get these eigenvalues and like plug it in.
But would you expect to be able to substitute the infinite width one modulo correction that you can still neglect?
Yeah, we've neglected that because that correction is like at t equals 0, there's some correction. And also it's like a random variable, but we kind of neglected that. I think that's what's being neglected. So this is my interpretation of this calculation. But it's sort of yeah. Does that help a little bit?
That's my question.
One more thing. Over here, you cannot really have number of samples to be growing with width, right? Because the moment they grow, you could have other terms that will come in the calculations.
There's
So it's to be constant in some sense.
it's sort of working still in this limit where number of samples is finite and width is kind of the largest parameter, and we just backed off of that. So I guess you could try to ask, if I track the m dependence of these various things, are some of them stronger than the others, perhaps? But I dropped all my 1 over m, so that would be actually, okay, I think I see what you're saying. Like there's a 1 over m that's coming from r, multiple r's, as you go down this hierarchy, perhaps?
Right, and also you're summing over all these samples in the data set.
Yeah, that's
It
this.
is linearly affecting.
Yeah, but that's okay. I haven't tracked it, but I believe this 1 over, this residual. There should really be a 1 over m every time you do this, and so it's kind of like order 1. It's not amplified by the size of the data set, and I suspect that follows through when you go down. Okay, so just to write basically the final answer, this is the correction. And then I promise I will not write too many more things of this form. Okay, sorry, that took up an entire board. But so what's happening here is I regrouped. Now x tilde is defined to be x1, x2. They're the two free samples on this thing. O3 has this third index that's being dotted into these eigenvectors. This is over the training data dotted into the eigenvectors. This has two free indices. The first two samples, x1, x2, are free, and the third and fourth one are being dotted into the vectors on either side. So this is like for every x1, x2, this is a matrix being dotted into this thing. These are all just regular dot products over the training set, and so on. So you have this thing, and then the fact that it's suppressed in 1 over n is kind of implicit in these things. And a nicer way of having written it, if I had done it from the beginning, was the fact that if you compute, O1 as a function of time, there are two kind of integrals. There's one integral that looks like dt of stuff, and then there's integrals, like this. So these sorts of equations, as you know, have these sort of nested form. Okay, and if you take t going to infinity, you see that you get some finite correction to this thing. So the kernel, the evolution of ft at long times is something that looks like plus times this thing where this is the large time limit of this.
The exponential part is not symmetric in INJ.
Yeah, I believe that's not true. Let me check my... I believe that's true. So this is lambda I plus lambda j, but this part is a minus. Okay? Any questions? Any unhappiness with the justification behind the calculation? So this is the t going to infinity limit of this thing. So this is kind of implicit also, I believe, in what Boris is going to talk about. Yes? So, where was the funny stuff that happened? It was the fact that I kind of dropped stuff based on initialization, but really what I should do is kind of solve everything together. Like be sure that the loss, increases is similar to NTK. Be sure that the loss increases in such a way, I think, that you kind of stay within the regime of validity in a way that's consistent with these other assumptions. Would that be a fair way of saying it? All of these corrections kind of go like this.
Yeah, somehow this was carried out, like, to get some more explicit as the training result in this book that I wrote with Dan and Show. And like that truncation you mentioned gets promoted to truncation over n and so on and so forth. But it's really the same kind of.
So maybe I can rephrase. It's this truncation that's based off of initialization, and so it's something that it kind of has to hold out for some amount of time, and it's probably true. You would imagine it's kind of natural for it to be true as long as the loss is going down rapid enough and other things. So there are interesting questions I think you can ask about this. I won't ask about it. Like this it was a function space point of view. What kinds of parametric models correspond to these sorts of things and so on. But anyway, to kind of just regroup, this gives you, when we talk about feature learning, if we define feature learning to be anything that changes the NTK, we could have, I think a lot of the researchers here are interested in very strong forms of feature learning where the kernel changes by a lot. But we could kind of imagine mapping out a little bit of a phase diagram where there are regions of, data and number of samples, number of parameters, and so on, where the change in the kernel is large and norm. Then you could also start to ask more refined questions, like is most of the change concentrated in the top subspaces and so on. So I think the word feature learning, maybe we could try to start to refine it a bit more in terms of how much does the kernel change, where is the change concentrated in terms of a spectral decomposition and things like this. So this is sort of, let me call it weak feature learning because it's small. And we're doing it perturbatively. But Boris is going to talk about basically doing some version of this calculation which is much more involved. I think he won't actually do it, but show you some techniques that are related to this, where now what we keep and what we drop is based on depth over width. Similar to what we did when we did calculations of Wick's theorem, where we not only in the first lecture, where we kind of tracked how it was scaled. Certain things were either amplified or suppressed with depth. So this sort of thing that I dropped, because I quoted this result of an expectation where we were only tracking the width dependence and not the depth. So that's going to change, and it makes the calculation much more involved. But anyway, even if you're unhappy with this calculation, from the point of view of rigor, I think this hierarchy is interesting to think about in terms of other ways that you could effectively truncate it. And I think it's an interesting kind of just point of view on, where you try not to reference parameters, at least in this. You just have these O operators, and you've kind of summed over all the parameters.
So I'm just trying to wrap my head around what does this actually do. Like, for instance, what am I learning from this book?
So nothing here. Not like this needs further analysis. So I won't present that because that's hasn't been done. But now it's an explicit form that you could go study, but it's the correction, and it's decomposed in terms of the NTK basis basically, and it's small.
Because basically, you wrote the correction, and like in order to compute it, like is that actually like simpler than training the network, or you see, I mean, this theta infinity, like how do I compute it in practice? I must plug in the data. Analytically
or numerically? Well, the strength is more that it's analytic. So if you really want to do everything numerically, maybe you don't even need equations. But if you want to go, I think what you're asking, if I want to go actually plug into this formula, it's actually somewhat involved. It's computationally difficult, and this is actually what makes it kind of challenging to check higher order corrections against real network evolution, at least when you do it in function space, because these O operators have they have high derivatives of the function, which are costly to compute, and then you have to contract them as well.
Because, I mean, when you say analytic, you mean analytic in terms of like extracting the dependence on the time.
Time and like NTK, eigenvalues and eigenvectors, and just the residual, and the targets are, in here.
Right, but
so it's
initialization and the data are still kind of explicitly in there.
They're in here. Yeah, they're in here from the NTK properties, and okay, I didn't do the last thing. Then you evaluate this, if you want to evaluate on a test point or whatever, then you can let it carry that through also. You could also imagine looking at the population version of this rather than the empirical.
Because yesterday we also averaged over the initialization, and here is just for fixed initialization.
I didn't average over the initialization. It's just implicit in there, so it's.
Well, we had this values with respect to the initializations.
We had these are evaluated at t equals 0. And so, but then I dropped things based on this expectation. And it turns out the variance of those, okay, I didn't write this down, but there was an expectation of stuff and then the variance of stuff, of that same thing. And the variance scales in the same way, or scales as a higher power, so the standard deviation scales in the same way. And so like everything that I dropped, both the expectation and standard deviations kind of scale similarly. I think this is, okay, this is, my reading of this paper. This is where the justification comes in. Other comments on this, rigor or otherwise?
Check this practically, because at small width we will have the correction terms which will be maybe also matter, and for large width it is computationally difficult to calculate the coordinate derivative.
That's right. It's hard to check it exactly computationally in this formulation, which is function space, because I think this is what you were saying. There are derivatives in here, and they're summed over all the parameters.
And you can't check for coordinate books because then the other terms would matter.
Actually, so the authors did check this. I didn't put this in slides. They did check this leading order term. And for small networks, so you have to take small sample sizes and things like this, and indeed it pushes you out, it matches the agreement with a real network further out in time. Does it go all the way to time infinity? No. But it's leading order. So it's hard to check in function space. You could check in parameter. You could do some version of this in parameter space, and those you could check. But actually, to my knowledge, there are empirical results where you take, say, high order Taylor expansion of the function about initialization. You instantiate that, and then you take a real network, and then you ask, how far out can I describe the real network out to long times? And actually, for a lot of the more reasonable settings, you can't. If you do this numerically, like you go to third or fourth order, and you get decent, pretty good agreement out to late times, but still you don't capture the full evolution.
Maybe I think this is going to lead into what you're about to talk to, I think, but it's also a little hard because this breaks down at large learning rates. If you want to see this, you have to take not too big of a learning rate,
Yeah.
because they're kind of annoying as well. So,
is it possible to see if this correction has some correction in the generalization hardware?
Yeah, so that's the kind of thing that I think what this buys you is that, we don't have a lot of, to my knowledge, fully, apart from NTK, one of the, in my opinion, one of the many nice aspects of NTK is that it's analytic. You get kind of, people have done computations with it, people have done a lot of theory with it. So I think, in my opinion, this is sort of the main, maybe, strength of this type of thing. Because if you said write down a closed form expression for feature learning, many of the ones that I know of have some sort of approximation in there. Maybe they initialize in a certain subspace and they write down something for deep linear networks or things like this. So that was one, motivation for presenting this.
Well, I guess it really boils down what we mean by closed form.
This you don't. This at least it's kind of we analyze NTK and targets assume some particular target distribution in NTK and decompose it into a basis. So, but you think.
I mean, I don't know. I mean, from kind of my statistical physics kind of take on this is that I always want to somehow have some model for the data and average over that as well.
Yeah.
Which here it explicitly depends on the data, which of course may be an advantage, but it makes it very cumbersome to somehow understand what's going on.
It makes it cumbersome, but do you mean it's kind of data agnostic, which is nice. So now, so far, I mean it is, but then you could go, yeah, analyze it, I guess. Anyway, I'm curious to hear more of your
for instance,
thoughts. But
questions like what needs to be true about the task and the data so that the feature learning is actually bringing something. Okay.
yeah,
We would kind of have to plug in the data and see how the correction actually improves the generalization error. That was the question over there. So is that what one is hoping to be able to do on that?
yeah. Well, with this, I mean, maybe we will never have a, for the other feature learning regimes, you don't have perhaps ever will we be able to write down a closed form solution, and so then you try to study the problem of, generalization directly. But the original premise of how I kind of started with this lecture series was, okay, there have been many beautiful lectures about just generalization, where maybe in the background there's some assumption about what the actual function is and weights. And here, this course is kind of motivated on, in which regimes can we do some lower order thing, or the thing behind that, which is write down, kind of figure out what the function is doing, and then you can analyze generalization. But of course, that's not that's difficult, and probably, I wouldn't say it's the best way, most general way to proceed, but it's just one angle.
Just to be clear, in this expression, these sort of second, third, and fourth order NTKs, operators, are sort of the empirical ones in initialization, right?
Yeah.
They're not some sort of like idealized thing you can calculate without instantiating a network.
So, in the way that they're written here, they're not. But in their, yeah, I think Boris will talk about this. I'm not sure, but you could imagine like trying to form maybe a deterministic version of this in some limit. I'm not sure. So like these are all kind of, yeah. Let me say, just for the purposes of this calculation, they're just add a nit, and they're evaluated from derivatives of the network.
Can I ask a question? Maybe also for Julia. Has anyone tried, in actual network, to track the evolution of this NTK kernel or the eigenvalue? Just to actually, can we compute? We
Yeah.
don't make any assumption. We just train.
Yeah.
And then I don't know if that's possible, but you would compute the NTK kernel at the current value of the
Yeah.
parameters you have, and you just check whether this actually is moving, not moving, if these eigenvalues are evolving.
I wanted to show some of it tomorrow, very little, but yes, there are some. I'm aware of 3 works that I can send you the references that do that, and they study basically what this empirical kernel does during training. Is that what you're asking? And
Yeah,
the
that's
finding is,
right.
right, and the finding is usually that first it rotates a lot, okay? So the kernel rotates in some metric when you measure, say, alignment, and then it expands.
So it moves.
It stops moving, it just, the norm increases, but it kind of doesn't move in angular space anymore.
So it's in motion, right?
There's motion, but only in norm, so to speak.
Is that cross entropy? So maybe I can add to that. I think there have been some studies. Oftentimes they've been medium scale studies, so not like not a large language model where they go track the NTK. I think right now, for instance, at Google, people are trying to build more tools where they could try to track these sorts of things. But then there's sort of a question of which regime do you want to study as a theorist, or even just to look at data, because we could always pick our thing. So if I pick, let's say in scientific computing, where I have maybe order 100 samples or 1,000 samples and a pretty large network, maybe I'm not too far from these Taylor series expansions and parameters, and I could even get better performance if I use the infinite width kernel. But then if you're kind of like if you want to be describing large language models, they're operating in a different regime. So the question is kind of like, with all these studies, everybody's kind of working in a different, I think, regime. And then right now, actually, I'll talk about yet a different regime where the change in NTK is kind of a particular form. So I think that would be nice to kind of have some agreement on, or like what happens where, and what is the thing that one wants to study or explain. Okay, so this was an example of what I referred to as perturbation theory, in the sense that it was perturbative in 1 over n, but I didn't tell you anything about the time dependence. So in the sense that, like, just to recap, it was like perturbative in this sense, the sense of the width, but like time dependence, some could blow up more than others and things, and I didn't say anything about that. Okay, so let me just tell you some things. This is, let me make a claim that from some of my own work where we look at gradient descent in wide networks, but with large learning rates. So with some combination of, I'm going to give some minimal models for this, but also the real support from this comes from experiments. And I didn't prepare slides to show you because I thought we won't get to it, but let me just make some claims that are also, you can see in empirics. So if you train, you're working at large N, then you will find the following observation. So if you, let's say the network is wide enough, there's a learning rate, which I'm going to call eta critical, which is approximately 2 over lambda naught, where lambda naught equals max eigenvalue of the NTK at initialization. Okay, so this is, in the experiments, I'm going to say approximately, and then I'm going to show you some minimal models with some exact transitions. Remember yesterday we had this kind of upper learning rate, which was 2 over lambda min plus lambda max. So usually lambda min is small, so that's approximately 2 over lambda max. So when you're kind of in this regime, you get something that, as you make networks wider, will eventually be described by NTK. Okay, and then empirically, you see some other learning rate, eta max, where in this regime, you find actually that the kernel changes by quite a lot. So let me write out kind of the phase diagram, some phase diagram over here. And this is about 2 over lambda naught. And this eta max, in this minimal model that I'm going to give you, is going to be 4 over lambda naught. But in experiments, it's somewhere, depending on what nonlinearity you use, it's between 4 over lambda naught and sometimes, larger values, 12 over lambda naught, things like this. But the distinction between these two regimes is that as n goes to infinity, the change in theta over the course of training. So let me write theta as t goes to infinity minus theta at t equals 0 is going to 0 as n goes to infinity. And then on this side, delta theta is something that's order 1 at the end of training. So this is something that we observed empirically actually over many different types of experiments, and then we wanted to explain it and kind of understand it also in relationship to this hierarchy. So actually it ended up being that we couldn't describe it with the hierarchy in some perturbative sense. So we tried to construct some minimal models that would capture what's going on here.
Can you explain why the critical learning rate is only approximately 2 over lambda max instead of exactly?
So, well, it has to do with me trying to relate it to yesterday's lecture where we had, the bound we had was really like lambda max plus lambda min. And lambda min is sort of small. So the thing that's been checked is sort of like 2 over lambda max.
But on a quadratic loss it's only the largest eigenvalue matters, and there's no limit.
Yeah, that's what I think. For the purposes of this work, that's true. but I was trying to connect it to this like bound that we result from yesterday.
By the way, this base diagram, is it based on the standard parameterization or independent of that?
Okay, good. So let's work in NTK parameterization. Just because that's the theory that I'm going to present, and then, but the experiments have been tested in both. We never really went back to analyzing standard parameterization too much, but you see the same sort of effect, where again you have to scale learning rates with width. But for today, let's work in just the NTK. Parameterization, and let me take the following model. So it's just a single hidden layer network. N is the width. Okay, so I'll come back to, we want to analyze the dynamics of this thing. And really we want to do it from the point of view of, okay, and we want to do gradient descent. Let me say gradient. So this is really, it's dependent on the discrete time behavior, and we have MSE loss, squared loss. So we want to track the evolution of the function with the discrete updates, and also track the evolution of the NTK in this discrete time. I'll come back to writing down those equations, but one of the problems with that for this general thing is that they don't obviously close. So this goes back to when you have these differential equations, or in discrete, continuous or discrete time, how do you effectively close them? Some truncation procedure, or you need some sort of assumption. So it wasn't obvious to us how to analyze that, how to close it. So instead, I'm going to do a very simple example that basically gives you some of the intuition for that. Even though there's no learning involved, there's no learning or generalization involved, it's just a dynamical effect. So let me just specialize to the case where the loss is just, so we have squared loss. It's f minus y on the samples. But let me just take a single sample. And then just for simplicity, let me also set the target to 0. The reason for this is just because the type of effect we want to study is the difference between like order 1 and order n effects. So this sort of, what the scale of the targets is, it's something that's order 1. We can kind of ignore it. You can put it in if you want to track things exactly. But this just gives you a sense of what's going on. And then we have this single, we have just x equals 1, so it's one data point. Okay, so now you write down, gradient descent for u and v. Those are your two variables. Let me just do that so you see. Okay, but we want to go towards function space. So you can write down equation for f and also for theta. Now, in this case, theta is just it's a single scalar, and it's equal to and so I'm going to just call that lambda because it has just one eigenvalue. And also, again, note, at initialization, this is order 1. At initialization, this is order 1. So if you write down the update equation for f, it looks like this. Okay, so this model is not very, there's no learning again. It's just going to be dynamics of it. And what's nice is we managed to close it. So remember, I wrote down, even if we went to discrete time earlier, I wrote down, okay, we don't just have, we have even higher order things because we need to plug in for the updates for the parameters. And I'll write down, maybe I'll write down this more general thing in a bit. But in this particular case, we got lucky and we could close the equations. So then we can say something, we can get some intuition for what's happening with this. Okay, so sanity check. First, let's set n to infinity. Okay, so I dropped this. I dropped this. I have lambda t lambda is constant. That's ntk. And then I have, did I write this correctly? Just that that f is decreasing. Lambda is equal to lambda naught. F is decreasing by this factor. And as long as eta is less than 2 over lambda naught, then this is f is gonna decrease, and f is just is like a substitute for the loss right now. So the loss decreases. Okay, so we have a sanity check that we recover ntk, like an ntk phase. So if we take n going to infinity first, and then we get exactly, something that is ntk, and then if we and we have this constraint, eta is less than 2 over lambda naught. When we back off of infinite width, so this term is small. So remember, originally everything is, this is order 1. This is order 1. Say that again?
It's one of them. Where is the 2 coming?
This is order 1, and this is...
No, where's the 2 coming?
So that's where the, so it's coming from the other side. So just that in magnitude, it needs to be less than 1. And kind of ignoring that the signs, maybe flip and things like this. So then, as you back off of infinite width, so this thing is order 1. So this is 1 over n. This is something, right now it's negative. And so the correction is small. And things converge, this is also small. Things kind of still, you get some of these 1 over n corrections. So this is like our perturbative regime that we kind of just analyzed, or close to it. Okay, now instead, let me pick this. So this is needed just so that this thing always has negative updates. If it starts to have positive updates, this will diverge. And so with this condition, what happens is originally this thing is large. It's larger than 1 in magnitude, and this we can ignore, it's kind of small because it was 1 over n initially. And so what happens is that f is starting to grow, or the loss is starting to grow. Okay, so the problem, it's going to continue growing basically because originally here now, okay, this is very hand-wavy as you can see, but it's just the intuition. This keeps growing until this term becomes a problem. Because originally this term is very small. We're just getting small corrections, but f is starting to grow. If f grows to be of order root n, then this term is order 1, and it's negative. So the correction, lambda changes by some order 1 quantity during that time period when that starts to be true. Okay, so let me, the problem is something like this. Let me write it as this happens on some time scale which is also log n. Okay, and then once that happens, this term, lambda decreases by some order 1 quantity from its initial value. And lambda decreasing actually allows this term to kind of become smaller again. So the problem was, all it needs to do is kind of decrease enough so that it kind of satisfies lambda is less than 2 over eta at some point, so that this term becomes small. And once this term, kind of the intuition is once this term becomes small enough, then we can have kind of the optimization kind of converge again.
What about the eta squared F squared?
So this term, I believe in this particular example, this term I think helps you because I think this thing is on the negative side. So this is like adding in something positive and making it smaller. So I think it's something that you don't have to worry about, basically. But okay, this is just like me trying to give some intuition. You could run this dynamical, 2-variable problem on a computer and check, or formally prove where like the transitions are. Basically what happens is when you look at, on this sort of time scale, what's happening with the loss is you start with some initial value and it actually increases before it goes back down, and eventually convergence happens, at long times. But during this region where the loss has grown, so f becoming of order root n makes the loss of order n, so it's large. During this regime, lambda changes by some order 1 quantity. So during this, actually, if you look at it empirically, this in real networks, this tends to happen very rapidly, like in the first 100 or so steps. So you get a large change in the kernel just during that period, and then after that, things start to kind of stabilize a bit more. So you see now why I called it non-perturbative, right? So it's different. It's something that if you tried to actually relate it back to the hierarchy, you would find that all of those terms that we looked at, their scaling with n starts to break. And okay, maybe there's a clever way to resum that using non-perturbative series, but that's like a future thing. So this is something that sets in when the network is wide. There's a question, which is what happens as you actually take n to be infinite. So it seems that if you allowed time to scale with log n as well, there's some kind of double limit that maybe you would be able to access this sort of regime even as n goes to infinity. But this is sort of something that lies beyond NTK. You kind of have to work at finite n, work with gradient descent to do this. To get this.
Can we make a comment? So there's a very recent paper by Nisha Belkin and this group, where if you take that NTK hierarchy wrote down, and instead of truncating at 5, you truncate at 3, but you only keep one of the leading order corrections.
They capture this.
They can show that this happens.
So is there? You told me that there's some eps. There's a strength to that comes in.
Yeah. So basically, like the strength of their correction is like 1 over n, and so they have to wait time, like log 1 over epsilon, for this to happen.
Okay. Cool. Okay, so very recent work. A relatively recent work building on this. So maybe I take back what I said about it being non-perturbable. But in this sort of thing, with what we've set up, the kernel changes by quite a lot, and I think the parameters change also by quite a lot because of that.
It's really non-perturbative. They have to have like a fixed, like they really have to work at the analog of finite n.
Oh, okay.
Yeah, for sure.
Then that's.
They view it in some kind of like epsilon a small way, but you can't see it, as you say, if you just formally send n to the epsilon.
Okay, cool. Okay, so that's kind of the takeaway. We kind of basically we analyzed a non-convex problem, but we did it through this sort of dynamical systems lens where we just had a few variables in this simple case. Now, I don't know if people would want to see me do this, but I can also just say in words what happens when you want to go back to the full model with data. Okay, so this helped us get some intuition for how you might analyze this thing, because this thing, if you write it out, has dependence still on U and V, and it's not clear how to close it. One approximation you can, or kind of thing that you can do, which makes some intuitive sense, is when you go to analyze the full form of this, what the substitute for this is something like I minus eta theta on the data, right? And so you're applying that, when this term is, when the learning rate is too large, what's happening is you're applying that large number of times onto f. So you're projecting f onto the top eigenvector mostly. Let's say you project onto the top subspace of theta. And so if you make kind of this, if you take those equations and you project them with this sort of assumption that f lies along the top subspace, you get just a reduced scalar equation, which actually starts to resemble this. So let me just write that reduced scalar equation. You get something that you have to look at things that look like this. So this is after I've projected where f is now, f tilde is f minus y, I believe. So you get things that look like, so this is, rho is some variable that involves taking the residuals and projecting it onto the different samples. So it's a scalar. I may be missing an f tilde here, so don't copy this. But you see that it's, even now it's still ugly. There's some dependence on rho still. You see that this 4 is appearing again, like it did in the scalar equation. And so if you do this kind of substitution where f tilde is now projecting onto the top eigenvector, you get an equation that looks like this, where lambda is now the top eigenvalue of the NTK. Okay, so this looks like our scalar equation, except that now you still have these rows here, which are dynamical variables. But you can kind of start to see how a similar, roughly similar argument might start to hold. Okay, so the kernel changes. You converge to a place where the spectrum lambda is smaller, because it's also adjusted to the learning rate that you choose, and things like this. So I think I'm almost out of time. Am I? Let me say one thing about phase transitions, because this is not something we studied in great detail, but these sorts of things I think are related to dynamical systems. There's like the logistic map, I believe, but certain kinds of dynamical systems that have phase transitions as you tune one of the parameters. So this one, I don't want to say phase transition because we didn't take n to infinity and we need the times to kind of go to infinity. Then time also scales with log n. But this sort of thing becomes sharper and sharper as you make n large. So if you do something like finite size scaling, right, which is how you numerically in physics kind of diagnose a phase transition. As I mentioned, you look at the change in theta on this side. It's going to 0 as n goes to infinity, and then you start to see something like this, where it's order 1 on the other side. So there's some connection with phase transitions here as well, we think, and you can do things like calculate a critical exponent for this, where the critical exponent comes from the, let's say, for example, the amount of time you need to converge, which diverges at this transition. But if you expand that time, I won't do that, you get things like, okay, T star, which is the amount of time, number of steps needed for convergence goes like things like this. So it has exponent 1, and you can expand on one side of the transition and the other and things like this. Okay. We also have a belief, although we can't prove, based on this analysis, that even as n becomes larger, so this happens. So first of all, I should say this coefficient we don't really know, because if you study it empirically, it's actually quite weak. So for realistic networks, this actually happens quite fast. But what we kind of think, just from, again, hypothesizing off of these equations, is that in this sort of regime, there's a rapid change in the kernel early on. But then after some point, you can kind of linearize the model again, in the sense that, as n goes to infinity, it would be sufficient to kind of mostly perhaps take the kernel, at this time and just have a linear model analysis there. But that's not something that we can prove. It's just some experiments we've done and things like this. Okay, let me end there. Is it right time? Yeah. Any questions about this? Okay.
Okay, if no questions, let's thank Yasaman.